Hello everyone, my name is Dr. Alobeidyeen. I'm an assistant professor in civil engineering department at Tafel Technical University in Jordan. I'm very happy to send you this pre-recorded presentation about my latest research about valorization of Pomace Lignin as a sustainable chemical admixture for cement-based. So starting with the background and motivation behind this research work. We all know in the late 20th century, the sustainability in construction became a global priority, and sustainability push in construction material is basically to explore bio-based, renewable admixture and alternative for cement-based application. On the other hand, here in Jordan, we have a problem as Jordan considered as one of the top 10 olive oil producer. We generated a large amount of this agricultural waste. We call it as olive pomace waste. This olive pomace is renewable, rich in lignin, and also has a potential for cement modification. Scanning the literature and state of art, we just found that exploring the full potential of isolating the olive pomace lignin, and I will just emphasize on the isolated lignin from this agricultural waste, because if you want to read a lot in the literature review, you will find that the use of olive pomace in cement modification is not new, but the isolating lignin is this is a novel use to test it and see the effect of it to the performance characteristics, especially in cement-based and mortar. And here I just want to point out that this is the third study in a line of research effort. Our beautiful work has established the LBL successful application in asphalt binder modification, and we also study the OBL performance, economic, and environmental evaluation in asphalt concrete pavement. Both these research effort has been published this year, and they will be on the reference list in the last slide of this presentation. Feel free to access them and know more details about the application of the olive pomace lignin OBL. The research objective. First, we want to characterize the olive pomace lignin OBL fundamental behavior as a cement admixture. Here, OBL is tested as a chemical binder modifier, not as a structural component. We are not interested to see the effect of OBL on the original mix composition or replace cement or sand in mortar, because we believe the lignin is an organic polymer. It will act differently versus olive waste byproduct like ashes, which sometimes replace sand, are successful because the ashes, despite being waste, it also has a mineral silica base, so it exhibits the pozzolanic activity. Next, we want also to quantify the mechanical properties development at versus dosages. After we track the mechanical property development, we want to identify the optimal dosage for maximum performance enhancement. Going fast to the experimental methodology, we have the material, the olive pomace, which sources from a local olive mill in Tafila, Jordan. We have the Portland Cement BCCM1 it's been supplied by Lower Jordan, Rashadi Tafila. We also will use the sand and mixing water to develop mortar later on. The experimental setup, it's basically, we have 3 stages. I will present it in the experimental design flowchart here. So the first stage, we focus on extracting the lignin. So this happened in our previous work, so I will not speak a lot about it. We have a chemical team that work extensively on this stage, And the final product is basically we extract the lignin as a dry basis. We have also run a lot of tests to characterize and validate this lignin, just like elemental analysis, FTIR, spectrum, and SIM images. So we can use this lignin later on. Stage 2 is basically what this research is about. We want to have the OBL modified cement base. So basically we add lignin as a dry base and mix it with cement, then with water to have the modified cement base. We use the dosages we use is from 0.1 to 2% by cement weight, okay? And then we test the standard consistency and setting time, the initial and final setting time. Stage 3 will be about testing the strength or focusing on strength testing. We want to see the performance on modified cement mortar, so we add also the lignin with cement and sand and water. The same dosages we use from 0.1 to 2% cement weight, okay? And we test the compressive strength by the ASTM specification. We develop all the value for all ages, all occurring ages 3 and 7 and 28 days, and also for the flexural strength 3 and 7 and 28 days. So for this slide, I will not waste a lot of time. This is about lignin extraction if you are interested. So it went through sulfuric acid and alkali treatment using an existing chemical research. We basically have the OBL, we mix it with the sulfuric acid and through the reactor and do some alkali and pH adjustment using an AOH. Finally, we have the OBL, and we use this specific methodology where the yield of this experiment was 100% of the total 35% of lignin in the olive pomace. We also have a lot of analysis to characterize and validate the OBL. If you are interested, you can go to our previous work and read more about the extraction of lignin. These are the two research I already mentioned and has been published this year. Experimental results. First, we will present the cement-based performance. So here we have two tests. The first one is a standard consistency test, which revealed that OBL act as a plasticizer. And as you can see from the table, the control base has a standard consistency of 28.5. This is typical for the type of Portland cement we use. And OBL addition is progressively reduce the standard consistency across all the dosages level. This reduction ranging from 2.5% up to 30.5% relative to the control sample. And also this reduction, we can categorize it based on the low dosages. As we can see, we have a water reduction. So when we use a low dosages level from 0.1 to 3% to 0.3%, we have the water reduction from 2.5 up to 6.8. This suggests that OBL is insufficient to achieve the complete particle surface coverage. On the other hand, we have the moderate to high dosages from 0.7 to 2%. We have achieved a greater water reduction, 15.8 to 30.5%. This is much higher, but we all know that the optimal will be OBL at 0.5% dosages, where we have it 12.3%. It is shown as a practical balance between the performance and the economy. And as you can see from the figure, we have the OBL dosages percent by cement weight with the standard consistency and the water reduction. We have the 0.5%, where we have a 12.3 water reduction as a practical balance. And the next test we done on the modified cement based is basically the sitting time. The results have been revealed that OBL absolutely act as a sit-rate trader, as you can see from the figure, where OBL progressively delaying both initial and final sitting time with the increasing dosages. So you can see the control base, for example, initial sitting time is 145 minutes. The final sitting time is around 240. This is within the typical range for this type of cement. So what we can see that we have an optimal dosages at 0.5% to produce initial sitting time of 195 minutes. It represents 32.41 increase. This is very acceptable for most construction application. And the final sitting time reached 325 minutes with the increase of 35.4% versus control sample. The final initial time ratio remained relatively constant. We have to point out this thing. It is 1.65 to 1.69 across all mixes. For this slide and the next slide, we will present the strength testing performance for the OBL modified cement mortar. We will start with the compressive strength testing. We done it for all mixes at all curing gauges, 3, 7, and 28. And as you can see from the result in the table, we have the control-based mortar typical compressive strength. We have 18.5 megapascal at 3 days, and 28.2 megapascal at 7 days, and 42.3 megapascal at 28. And what compressive strength testing shows for all the curing days is relieve a complex and dosage dependent effect of OBL on the mechanical properties development. So as you can see, we have the low dosages from 0.1 to 0.5, where mixes shows strength enhancement for all ages, the 3, the 7, the 28. The optimal one is reached at OBL dosages level 0.5. It basically 18 plus 18.86%. For the moderate, we have 0.7. It is still enhancement, but lesser than the 18.86. We reach plus 10.46% at the 28th day. The high dosages from 1 to 2% OBL mixes shows progressively declining strength, where we have severe reduction in the compressive strength up to negative 23.17 at the 28th day. On this slide, we will present the flexural strength testing for the 3, 7, and 28 curing days. As you can see from the table, we know the control base has a flexural strength of 3.2 megapascal at the 3 days, 4.8 at 7 days, and 6.5 at the 28 days. The OBL addition also influence flexural strength in dosage dependent manner, similar to the one we have it in the compressive strength. So we have the low dosages, which shows progressively improvement in the flexural strength. The optimal one is 0.5, achieving increasing about 21.45% at the 8 days, exceeding compressive strength. This is very important. So we believe from this that the OBL microstructure refinement particularly benefit tensile flexural performance compared to the compressive strength improvement. We have the intermediate and high dosages from 0.7 to 2. This has shown declining strength, where we have the severe reduction, negative 28.23% at the 28th with OBL 2% mix. So for our last research objective, we want to identify the optimal dosages level for OBL to be incorporated with the cement base and cement mortar. The study is interested to use a weighted multi-criteria decision analysis. This analysis achieving the increase, these percentage increase of the compressive and flexural strength. We already present them before. We have also the 12.3 water reduction potential and 32.41% initial sitting time increase. It's about 192 minutes. This is acceptable. All these convergence of this multiple optimization criteria lead us to the dosages, the 0.5% dosage provide the high confidence in this recommendation for a practical application. So to finish our presentation, we have here the conclusion. First, OBL function as a double action admixture as a plasticizer and citrator in cement-based system. The optimal dosages for OBL identified to be 0.5% by cement weight. It increased in compressive strength in the 28 compressive strength from 40 to 0.3 megapascal for the control sample up to 50.2 megapascal. It also increased on flexural strength from 6.5 megapascal for the control mix up to 7.9 megapascal. It also shows a 12.3 reduction in standard consistency, enable water reduction or workability improvement. This is very good. And shows 32.41% increase in initial sitting time, remaining within acceptable construction timeline. Finally, thank you so much for listening to my presentation. If you are interested in this area or research topic, you can reach me using my contact info below. Thank you so much.